Hello, and welcome to a second lecture on directivity of apertures. My name is Steve Ellingson. Here's an overview of this lecture. First, I'll remind you about the aperture synthesis example that we did in a previous lecture. This was a 10 gigahertz phased array, and we're going to continue to discuss this example. Specifically, I want to raise the question of how to compute the directivity of this thing that we have designed. I raised that question in the original lecture on this example, and now we're going to follow through on that thought. Part of the answer will involve discussing the directivity of an ideal sector beam antenna. Then we'll derive the directivity of a Huygen source distribution in an aperture. Our original design example involved the assumption of a Huygen source distribution, so this is really coming up with a formal and exact solution for the directivity. And then we'll apply all this to the design example. Okay, so here's a reminder about the design example. It was a planar array in the z equals 0 plane, so the aperture was in the xy plane. Operating at 10 gigahertz, I specified that frequency for two reasons. One is so that I could show physical dimensions, in other words, meters in the aperture plane as opposed to just wavelengths. And also because 10 gigahertz, that is X-band, is a fairly common frequency for doing this kind of work. So just to add a little bit of realism to this. The array was designed to achieve a sector beam arrangement. So this particular sector beam that we designed for provided uniform directivity over a square patch in solid angle. That is angles between 10 and 20 degrees in theta and plus or minus 5 degrees in phi. This was the aperture distribution that we came up with. This is the magnitude of the magnetic currents that we derived as the answer to this problem. And then to obtain a phased array, of course, we would just simply sample this aperture respecting the Nyquist criterion, and those would become the weights of the elements in the phased array. Here's one of the plots that I came up with by then taking these magnetic currents and plotting the fields. So this is the magnitude of the electric field as a function of theta in degrees. And I showed you, in fact, that this does produce a sector beam, something which has approximately uniform directivity over the specified region. And it wasn't exact, and the reason it's not exact is because we're truncating the distribution. The distribution that's required to actually create this particular pattern requires currents that go off to infinity in all directions. So by truncating that pattern, we end up with a variation over the specified range and then also side lobes. Okay, so how to compute the directivity of this thing? Well, if we go all the way back to the beginning, you remember that a generally applicable procedure to compute directivity is to first take the aperture electric fields, let them radiate into the far field. Once you have the radiated fields, then you can compute the normalized patterns. Once you have the normalized patterns, then you can compute the beam solid angle. Once you have the beam solid angle, then you can compute the directivity. So this was a very general procedure. I also pointed out that for apertures having maximum directivity in the broadside direction, that is a beam pointing directly along the z-axis, well, you could also compute directivity this way by integrating just over the electric fields and then squaring the result, and then also integrating over the square of the electric fields in the aperture, taking the ratio, and this turns out to be a measurement of effective aperture. And then if we have effective aperture, we can get directivity using the normal expression. And this was attractive because it's relatively simple to do. These integrals are just over the aperture, whereas this is an integral that's volumetric, and this is an integral that's volumetric. So this appears to be somewhat simpler and faster to compute. The problems are as follows. First, this is very computationally intensive. Now, in the year 2016, this is rarely a problem. However, maybe it is. Maybe you're trying to do a design iteration that requires you to do thousands of these calculations. Well, if every calculation requires 2 integrations, then that could be an issue. This simplified form, or the somewhat more attractive form, turns out not to be valid in our design example. Why? Because the beam pointing direction is not broadside. So one of the things we'd like to do here is extend this kind of result to the more general case where we have an aperture and we'd like to integrate over the aperture, but perhaps the beam isn't pointing directly broadside. So I'll remind you that many lectures ago, when I was talking about directivity, I showed you a simple example. And the reason I showed you this example earlier was because it was to give you some practice computing directivity, but it's convenient for setting the stage for what we're about to do. In this example, I said, imagine a phased array. And imagine this phased array is producing this thing. I didn't call it a sector beam then, but you can see it as a sector beam now. It's something that has uniform directivity over a range of angles around the z-axis and is 0 everywhere else. And this was easy to work out because the beam solid angle is simple to compute. We find out it's 2 pi times the quantity 1 minus cosine theta naught, where theta naught is that beam opening angle. And then the directivity is 4 pi over the beam solid angle. So we found that the directivity of this thing is 2 over 1 minus cosine theta naught. So it would be convenient if we could come up with a similarly simple and straightforward expression for any sector beam, including the one that we have been using as a design example. So let's do it. Here is the calculation for beam solid angle. If I have a sector beam, that simply means that the normalized pattern is 1 inside a specified range and it's 0 everywhere else. So I can represent that just by limiting my integration to the specified range of theta and phi. And then I quickly find that the beam solid angle is the quantity cosine theta 1 minus cosine theta 2 times the quantity phi 2 minus phi 1. And now I can compute directivity. It's just 4 pi over beam solid angle. So I find the directivity in this case is 4 pi times that quantity, cosine theta 1 minus cosine theta 2, inverse, and then multiplied by phi 2 minus phi 1 inverse. So very straightforward expression. We can apply this to our synthesis example. In our synthesis example, theta 1 was 10 degrees, theta 2 was 20 degrees, phi 1 was minus 5 degrees, phi 2 was plus 5 degrees. So the directivity turns out to be 32 dBi. So this is obviously convenient for a number of reasons. One is it's very simple to compute. It also tells us what the ideal value is. In other words, if we were able to achieve a design which gave us exactly the specified pattern, we would know right away what the directivity was. We can also use this as a way to check our results. If we compute our directivity exactly using some method that allows exact computation of directivity, then we know that it should come out to be pretty close to 32 dBi. And things like truncation of the aperture and other things should still give us something in this ballpark. Shouldn't be radically different from that number. Note that this result implicitly assumes that the array will be infinite in extent, but is not necessarily an upper bound, right? So this solution doesn't know anything about limits of the aperture. It's simply saying that if you do manage to achieve a sector beam with ideal characteristics, then this will be its directivity. I will show you, though, that this is not necessarily an upper bound. In other words, it's not really the best possible directivity we can get. You will find, and this is perhaps counterintuitive, that you can get sometimes better directivity by making the aperture smaller. So I'll plant that seed and then we'll come back to this later. Now, as promised, I would like to work out the directivity of a planar Huygen source distribution. Remember, our synthesis example assumed a Huygen source distribution, so this will be relevant. Directivity, 4 pi over beam solid angle. Remember that beam solid angle is total power. That something has units of watts, divided by radiation intensity. That's something that has units of watts per steradian, right? And you divide those two things, you get steradians, which is beam solid angle. You will recall that maximum radiation intensity can be given in terms of the power density times the distance to the field points squared. And for that to be the maximum radiation intensity, it has to be, of course, in the direction in which the beam is pointing. And we can write power density as the magnitude of the electric field squared divided by 2 times the wave impedance, right? And this 2, remember, is indicating that we're using peak units. Otherwise, if we were using RMS units, there would be no 2 there. And then remember, for a Huygen source distribution, this is the electric field, right? It's plus jk, phase factor divided by 4 pi r, no obliquity factor, the spatial Fourier transform of the magnetic currents, and then the polarization vector. So now we can make the substitution, and we find that the maximum radiation intensity is given by this expression, right? 1 over 2 eta, that comes from here. Then the magnitude of E squared, I've just plugged that in here, and then R squared. And of course, this cancels with this, as it must, because the maximum radiation intensity should not depend on distance. Here I've rewritten the equation on the bottom of the previous slide here. Just evaluating this a bit, I can pull out some constants, and I find that I have 1 over 8 eta lambda squared. Remember, here I've used 2 pi over lambda as the wave number, times an obliquity factor squared, times the spatial Fourier transform of the magnetic currents magnitude squared. And I can substitute the expression for that Fourier transform in here. And remember, this is an integral over the aperture. Now also, remember that power, total power, is simply total power flowing through the aperture. In other words, we can compute total power from the antenna in any number of ways, just as long as we capture all the power. For an aperture, we know all the power must come through the aperture, so it's sufficient to integrate the electric field over just the aperture in order to capture all the power. And then also you'll remember the boundary condition that applies here, which turns out to be here, the relationship between the electric fields in the aperture and the magnetic current distribution. So we find that the total power is just 1 over 2 eta times an integration of the magnetic current distribution in the aperture magnitude squared. So now we put this all together. Directivity is 4 pi maximum radiation intensity divided by total power. I simply divide the two expressions that I have derived in the previous slides, and I find that the directivity is pi over lambda squared times the square of an obliquity factor, and then a very familiar, hopefully, looking expression. It's the integral over the currents, magnitude squared, over the integral over the square of the magnitude of the currents. Right? Very similar to an expression I showed you earlier in this lecture. But this is exact. This is not an approximation. And you can check to make sure it's right a number of different ways. One way is to make sure it's dimensionally correct. I encourage you to do that. Also, you can check to make sure it gives us the right result when theta naught is 0. That is when maximum radiation intensity is pointed broadside or when the beam is pointed along the z-axis. Those statements all mean the same thing. So you should be able to compute that for this expression and find that gives you the expected result. Now it's time to apply this to our aperture synthesis example. So I'm computing results for the example. The vertical axis here is directivity in dB. The horizontal axis is side length. So here we're saying how big one side of the aperture is. And of course it's a square aperture, so both sides have the same length. We worked out one expression for an ideal sector beam. In that case, we found the result was 32 dBi. So there's that line here. However, we also have the exact expression that we just derived, and we can plot that too. And remember, that's now taking into account the finiteness of the aperture. When we do that, this blue curve then shows us what happens. What happens is, of course, the directivity is very small if we only use a small amount of the available distribution. But as the aperture gets bigger, the directivity shoots up. So by the time we get to about half a meter squared or so, we're very close to the ideal directivity. And then, of course, there's some wobbling around. So here it's bigger, here it's smaller than the ideal result, here it's bigger than the ideal result, here it's smaller than the ideal result. That is simply another expression of Gibbs phenomenon. So what we're seeing is that as the aperture gets larger and larger and larger, we get a result which eventually converges to the ideal result. No surprise there. Okay, so there's some relatively profound things that emerge from this result. First, directivity is not proportional to area, except when the array is relatively small. In other words, here's the array size increasing, and we see that the directivity is increasing. That is as expected. But then we see that there's some threshold aperture size, say about half a meter by half a meter, where we stop increasing directivity in proportion to size, and instead we start oscillating around the theoretical or ideal value. So it's only when the array is very small do we see what you might consider intuitive, which is directivity increasing with area. Now, this is not to say that any aperture shows this property. What's happening here is we have a sink-like distribution of currents in the aperture. So it's not surprising that most of the benefit comes from the center part of the aperture, because that's where the magnetic currents are the greatest. And then as the extent of the aperture gets larger, we get less and less benefit because we're including currents which are smaller and smaller. But as I've pointed out, most of the directivity actually comes from a relatively small area. By the time you've gotten to about 0.5 by 0.5 meters, that is just a quarter of a meter squared, you've got most of the directivity. Now, that doesn't mean you've got a very good sector beam. It just means that with whatever beam you get for an array that's this size, you've already got most of the directivity. So that's most of the sensitivity in a receive application and most of the power density in a transmit application. So this is a useful design insight. Increasing area beyond this kind of threshold amount of aperture simply serves to reduce the Gibbs phenomenon. Right? So as the area of the array gets larger and larger from this threshold here, all we're really doing is reducing the amount of Gibbs phenomenon. So that's not necessarily a trivial thing. We may feel strongly that we want the best possible looking beam. And if that's the case, then there's good reason to make the aperture larger and larger. But if you're not so concerned about the directivity being utterly constant over the sector, then this would be a foolish thing to do because you're simply making the array larger. So, some concluding remarks. In this lecture, we have introduced two new tools, which are useful especially for off-broadside pointing systems, which was something that we were missing in our previous expressions. The directivity of an ideal sector beam antenna, a very simple expression, but useful to have. We've also worked out an exact expression for the directivity of any aperture in which the electric and magnetic equivalent currents are related through the Huygen source constraint. And that's a very, very broad class of apertures. You might even say that's almost general. We've also achieved new insight into how to select aperture dimensions. In particular, we found that bigger is not necessarily better. We got most of the directivity from a relatively small aperture, and making the aperture bigger and bigger was simply making the beam look nicer and nicer. So how large the aperture should be depends on how strongly you feel about the trade-off between those two things. Do you simply want to achieve a certain amount of directivity and have the smallest possible array that can do that? Or is it really important that the directivity over the sector be as constant as possible? And you can imagine that similar thinking could be used to guide the design of the shape of the array. We've limited our discussion to the size of the aperture, assuming it's square. But what if we made it rectangular? What if we made it elliptical? Now we have a simple scheme that would tell us how to optimally choose the shape of the aperture. This concludes this second lecture on directivity of apertures.